do have a sore throat, so my voice will deteriorate over time.
I can speak for you. No.
Joe can always speak for us. Okay. We've done a question like this before. I want to start with something that's familiar before we move on to a new concept. The question was, how many ways is there to go from section A over to section B here? Right? And I can try to highlight a few of them just to remake a point. Like you could go all the way over and then down. That's one way. In theory, you could go like a little bit of each, kind of zigzag through the middle. And of course, it auto defines it. Never mind that. You guys get what I'm saying here. We've already learned how to solve this one. If you guys have forgotten, though, let's just do a quick recap. I guarantee you that you've got to go right, 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 and down, down, down at some way. You have to take 7 blocks total. So the correct answer to this was 7 factorial over 4 factorial, 3 factorial. Is that familiar to you guys? That's the kind of question they might give you. What I want to do is I want to take the principles that someone managed to learn from solving a question like this and apply it to something very different. What we're going to do eventually, and I've got to get to the slide, but I want to show you how to be able to expand x plus y to the power of 7. And I'll show you how to do that really fast. Okay. Now, if it wasn't to the power of 7, if it was x plus y squared, you would just write it next to itself, x plus y, and you'd FOIL, right? But if I make this to be the power of 7 or 8 or 9, it's going to take a long time to FOIL the crap out of one of these things. You know what I'm saying here? Well, someone discovered that, as weird as it is, this concept right here can actually be used to help you FOIL things. And so that's my goal. By the end of the day, I'm going to show you what's known as the binomial theorem. The reason why we call it a binomial is because I'm going to give you, like, say, an x plus a y, and we're going to want to go to a power of something, like square or cube or fourth, and I'm going to show you how to distribute a binomial much quicker than just FOILing it. Fair enough? Well, the reason why I can't is that we haven't actually learned the previous background of how to use combinatoric stuff yet. That's why it kind of has to go here. But it's a very odd section because what we're going to do right now is algebra. But rather than doing algebra and actually like do a whole bunch of FOILing, I'm going to show you how to save time using combinatorics instead. So that's my point. So you have to bear with me though because I have to kind of guide you there. So I want to start with this example here. Anybody ever watch The Price is Right? You ever seen this show? The Price is Right. Oh, it used to be like a classic, like Bob Barker was the guy. Now it's Drew Carey, where like they go on and they have to like bid for prizes. No one's ever seen this show?
It's like guess.
Yeah, you have to like guess what the price of things is. Okay, so some of you know the concept. Okay, this is one of the little mini games that they have on here. It's called Plinko. And basically the concept is you earn some of these tokens. And you can see with the photo I snagged here. Here's one of the little tokens right here. Yeah. You walk up to the top of the stairs and you put the token wherever it is you want.
I play that all the time in the building.
Okay.
You were on the Price. No, it's not.
But like, it's probably a similar concept though, right? Because what ends up happening is you like, let's say you start the little guy right here, right? Well, what could happen is it might bounce this way for a little while, then it might go this way for a bit, then this way, and eventually it lands in a spot. And like if it lands right here, then you get nothing, right? But if it lands right here, then you get 10,000.
I always get
You're very good at this job. Okay. What I want to do here is imagine this same scenario is actually the pathway problem, only it's been rotated. Can you see that? This Plinko right here, when you put it right here, basically it has two choices. The disc could either fall this way or this way. And I mean, based on random physics and how it just seems to go, it might go all the way down this pathway and then come back and go there. And so the most likely possibilities are sometimes over here on the sides. Does that make sense? And that's why they don't pay out very well right here. The one right in the middle here, the 10,000, they put zeros on both sides of it. So that like, as you're like sitting right here, it could either go left or go right. You either could win 10,000 or nothing, right? But in a way, this is a pathway problem. And I want to show you another way of solving a pathway problem. And so I've just got some few examples right here. So again, imagine a scenario of Plinko, but it's twisted sideways, but it's the same idea. We want to go from A to B. Now, we already know the answer to this one using combinatorics. I've already shown you how to do this one. The answer to this is going to be, 8 over 5 and 3. Are you okay with that? Someone grab me a calculator. This is, by the way, 8 choose 5, or it's 8 choose 3, either one. Someone find me what that is real quick, just so we know what the right answer is. Okay, I want to show you another way of solving this question. And again, keep in mind, my whole point of my lesson is eventually showing you how to factor things faster. But I have to build my way there, okay? So here's another way of solving it. Let's say that you were just to count intersections. Like right here is a node, an intersection point. Right here are all of your nodes as well. Very similar to like as the this thing right here. Here's like one of those little nodes in the middle there. That makes sense? My question for you is, how many ways, if you're starting right here, is there to get to this node here? And at first this is going to sound dumb, so bear with me. But the answer is, well, there's one way to go here. The only way to go there is to literally go that way there. How many ways is there to get to this node right here? Also one, because the only way to get to this node right here is to literally walk all the way there. Bear with me. What if I wanted you to tell me how many ways there is to get to this node here? The answer is also one, because you literally just walk in a straight line. Well, let's say we talk about this node right here. The answer is two. And you can visually see it because you could have gone this way and that way, or, keyword, you could have gone this way and that way. Well, or means add. So if I found one way to go this way and one way to go this way, by adding them, there's two ways to get to this node right here. Well, someone really smart eventually figured out, hang on, I'm just adding numbers. If there's one way to go here, or there's two ways to get here. There's one way to go here, or there's two ways to go here. To get to here is three, because this one and this two merge at three. So watch me finish this first one off here, because I've got 4 examples to show you. But watch me finish the first one off. I'm going to prove to you how I got 56 another way. There's only ever one way to go around an edge. All of the nodal intersection points around the edge has to be 1, because literally there's only one way to go in those straight lines, right? But now we start adding the sum of numbers. Like this 1 and this 3 makes a 4. This 1 and this 4 makes a 5. This 1 and this 5 makes a 6. Keep watching. 1 and 2 makes 3. 1 and 3 makes 4. 3 and 3 makes 6. 4 and 6 makes 10. 4 and 6 makes 10. 10 and 5 makes 15. 10 and 10 makes 20. 20 and 15 makes 35. 15 and 6 makes 21. When you add 35 and 21, you get 56. Now, most people would sometimes actually start by showing you this concept, but I actually started with showing you the combinatorics process. But once you realize that they're one and the same, that really I can use combinatorics to solve a complicated problem like this, eventually someone figured out the link between this and factoring. So, but again, I want to build my way there. So, let's try the same thing on this one here. Well, let's actually count them first this time. Rather than knowing the answer by doing something, choose something, let's just count the answer. So everything along the edge, all of your intersection points are 1 along this edge here, because there's only one way to go there. And then after a while, you pick up on the pattern. 1 and 1 makes 2, 1 and 2 makes 3. So I'm just going to start doing it. You guys let me know if I lose you. Be 84. $26.94. 210. So I got 210 in the bottom corner by literally counting up nodal points. If I use that term nodal points, that makes sense to you guys? Most of you took physics with me. Now, the faster way of doing it, though, would be to say that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 blocks. And I don't care which order you choose them in, but you need to choose 6 of them to go to the left, which is 10 over 6 and 4. And ideally, that should give us a same number. So far, so good. Okay, next twist, though. You guys can see that both of these ones right here, though, are not perfect rectangles. Because what we've done is we've cut out some sections. So, like, if you can apply this to a real-world scenario, imagine that your job was to be the designer for a town, or you were in charge of traffic control. And it was your job to figure out, well, how many ways can we make it to get from the west side of Lethbridge to the Walmart on the south side? I don't know, that just comes to my mind, right? And so here's all the paths you have. Well, what happens if right over here you can't build roads because there is a lake in the way? Does that make sense? Well, now we have exceptions. Clearly, this is going to be less now because of the fact that there's like some gaps here. And what it means then is that we can't actually use this method up here of choosing and picking. Because in a way, let me fill out the dots here. I'll show you what makes it different. There'll be ones along these edges here. It makes that 2. Makes that 3. That makes that 3. And makes that 6. Are you okay with that first little bit? There is 0 ways of getting to there. Because literally there is not a road there. 0 and 6 means there's still 6 ways of getting here. And there is 0 ways of getting here, which means there's still 6 ways. You can see how that works there? It means that there's 6 ways along both of these edges because of the fact that this is out of bounds. There's no way to get there, so then 6 and 0 still adds to 6. The problem then is that we can't use like 6 pick 3 or something like that because it doesn't quite work in the same way, so we have to do this the long way. I got 210 when I eventually finish this thing off, so let me know if you guys don't.
Victor Wadsworth, can you please come to the office? Jessica Wadsworth, please come to the office.
Yeah, 210. Now, I can't solve this question, by the way, with like a choose formula. The reason why a choose formula won't work is that all of these zeros right here, because like there's no way to get to this out of bounds territory here, there's really no way to account for that. So really the only way otherwise is literally just to count it up, which is annoying. So if it's a perfect rectangle, you can use this formula up here. If not, you literally have to count them. So why don't I try one last one here, and then we're going to move on to how this principle got used in factoring. So again, I'd go with 1 around the edges. And maybe you guys will get to about there. Okay, if you're okay with where I've written right here, there is 0 ways of going to any of these like kind of spots here because that's out of bounds for whatever reason. It's not valid, right? So then this corner right here that I'm pointing at is still 10. Does that make sense? Because 10 plus 0 is still 10. And so these edges will remain 10s. I got to 200. Cool. Okay, now, history lesson here. I'll make sure I tell it right. What's his name again? It was Blaise Pascal. I've actually told you a story about Blaise Pascal before, probably. Legend has it when he was in grade 2, he was bugging his grade 2 or kindergarten teacher, like sometime in elementary school. Maybe you've heard this story. And so the teacher, basically as a way of getting rid of him, told him, add up all the numbers from 1 to 100. And you got to keep in mind, this was back like hundreds of years ago before a calculator, right? So she expected this was going to keep him out of her hair for like an hour because he was being a little brat, right? And he comes back in like 2 minutes and he says he's got the answer. And the teacher's like, no way. Because like she needs to like literally use like an abacus or something to add them all up. You know what I'm saying here? And if you remember the story at all, if I've told you this before, Pascal realized that adding 1 plus 2 plus 3 plus 4, all the way adding up to like 97 plus 98 plus 99 plus 100. Do you guys remember this story at all? How did he solve it? You guys remember? He paired them. Yeah. He said that 1 and 100 adds up to 101. Sorry, I'm a mess here. 2 and 99 adds up to 101. 3 and 98 adds up to 101. 4 and 97 adds up to 101. Until you finally get to the middle, where you get 50 plus 51, which also equals 101. He then realized that he had 50 pairs, because he had from 1 to 50, each having a doppelganger, and each of them added up to 101, and he just did that, and he got his answer. Anyways, that's not relevant to the story here, but this is about Pascal. Like, he was a brilliant, brilliant mathematician. And he realized something similar to what you guys might pick up on right here, is that there is a pattern to this. I want you to imagine the Plinko problem again and tilt your head sideways. Okay. Look at this. It always goes 1, 1, 1. I'm going to do it in like rows like this. First row is 1. The next way, it's 1, 1 again. And then it's 1, 2, 1. 1, 3, 3, 1. 1, 4, 6, 4, 1. And as we worked in a lot of these problems here, it had the same sort of thing over and over, didn't it? 1, 1, 1. 1, 2, 1. 1, 3, 3, 1. Now, granted, we're missing some numbers, but I mean, there is still the 6 and the 4 right here. There still are the 10s right here. Can you kind of see that sort of pattern? And if you flip it sideways, like the Plinko problem, I'm going to go back to here. You realize there was a pattern to this. So imagine that you started your Plinko chip right here. Well, then there's one way for it to go just down the, down the sides here. That makes sense? If you start it right here, there's only one path for it to get to here. But it's actually more and more likely for it to get to, like, say, there's like, say, 2 ways to get here. It can go that way here or that way. There's 3 ways to get here. There's 4, 6, 4, 1, 5, 10, 10, 5. Does that make sense? Now we can actually see a little bit of this math in the Plinko problem. Where is the most likely spot for it to land up at? Well, actually, the most likely spot is actually in the middle, because you can see the numbers are getting bigger as you get towards the middle. However, because of the fact that if we were to keep going, this would actually eventually be 1, 6, 15, 20, 15, 6, 1. This one right here is 20. Sure, the most likely thing is 20, but collectively, 15 and 15, the ones that pay off as 0, are collectively more likely. Does that make sense? Okay, so cut that aside. That was what Pascal discovered. Now I want to talk about the factoring bit. So what we're going to do here is, this was known as Pascal's triangle, and I've kind of been showing you this in like a tilted direction. It has this sort of pattern to it. Okay, now I want to do a simple, silly exercise here. We're going to do some factoring. So kind of break for a second here, and we're going to do at least the first 3 rows. We might not even do the next one here, and we're going to discover a pattern. Watch this. If we were to FOIL this out, it's going to give you x squared plus 2xy plus y squared. Is everybody able to do that first one in their head? Yeah. 1, 2, 1. You've maybe already beat me to this. If we were to FOIL, let's just FOIL one more. Let's say you FOIL that by an extra x plus y to give us this next one right here. Here's what you'd get. You get x to the 3. You get 2x squared y. You'd get 1xy squared. You'd get 1x squared y. You'd get 2xy squared. And you'd get 1y to the 3. So I basically, if you can't follow what I did this times this times this, and then this times this times this. I FOILed it out, so I got 6 terms. Assuming you agree with all my foiling here, let's combine like terms. What we have then is 1x to the 3. What's this guy here? This guy and this guy right here. There's a 3x squared to the y. This one right here and this one right here, there's also 3 x's with the y squared. And then there's 1 y to the 3rd. Look at the coefficients. 1, 3, 3, 1. 1, 2, 1. 1, 3, 3. This is what Pascal realized, is that if you had to FOIL something out that would be annoying, we can actually save some time now. Because of the fact that I know that we're now going to be on this row in the table, I can tell you what the next row is going to be really quickly. It's going to go 1, 4, 6, 4, 1. So you're going to have a 1, a 4, a 6, 4, and a 1. And now I just need to figure out what the 5 terms are going to be. If the first one used to be x to the 3, now it's going to be x to the 4. And I'm going to do the backside as well. If the backside used to be y to the 3, the best it'll be is y to the 4. Now, I've already tried to prep you guys a little bit for this in other questions. If you've done them before, there was one about like doing heads and tails with a coin. Or I've also talked about the way that you can have like boys and girls in a family. right here you have 4 x's, and in a way, you actually have no y's. And right here you have 4 x's, and you have 4 y's, and you have 0 x's. Well, right here, then what we need to have is 3 and 1. Which in the middle would be? Yeah, you have an even split. Sorry, let's make that x, y2 and 2. Then this one right here is going to be, let's say, like 1 and 3. Now, some people might say, well, what if I wanted to go with the 3 y's and the 1 x right here? You see how it's symmetrical? It wouldn't matter if you flipped them around, right? Because what you need to have here is the 4 and 0 possibility, the 3 and 1 possibility, the 2 and 2 possibility, the other 3 and 1 possibility, and the other 4 and 0 possibility. And now you can FOIL it out really fast. All you have to do is know Pascal's triangle. Does that make sense? Okay, one more thing though. It means that you have to know Pascal's triangle. So if I want to do the next one, I'm going to do the next row. 1, 5, 10, 10, 5, 1. So if I want to do one more here, then it would be 1, 5, 10, 10, 5, 1. And so then we just need to fill in the rest. If it's the power of 5, the best you could do is all 5 of them are x. Then you could have 5 things where x is 4 and there's just a single y. You could do 10 of them where x is 3 and y is 2. 10 more where x is 2 and y is 3. This is the, got a doppelganger on the other side. This is where you have 1x and 4 y's, and then that one's all y's. Isn't that incredible? And that's so much faster than distributing. Because I mean, this would have taken forever to literally FOIL over and over and over again. So herein lies the problem then. In order to solve this, if I want to figure out the next row, which I think is my next question right here, let's say we wanted to solve this one here, it's actually really easy. Am I okay to flip sides, by the way? Just give you a second. If we were to do this one right here, I can tell you how this is going to look. We're going to need a y to the 6. We're going to need some y to the 5s with an x to the 1. I'm actually going backwards, but that's okay. I'm going to need a y to the 4 and an x2. I'll need a y to the 3 and an x3. I'll need a y to the 2 and an x to the 4. I'll need a y and an x to the 5, and I'll need an x to the 6. Makes sense? Those are all the terms that I'm going to need. The question is, how many of each am I going to require? Now, you could use Pascal's triangle. I want to show you one more thing here. So when you're done writing this out, I'm going to flip back slides. So make sure you're good here. I'm going to look at Pascal's triangle right here. I'm going to grab a calculator and do it side by side here. One more thing that Pascal realized is that just like with where I started class, this relates to combinatorics. The first row, I'm going to go with 0, choose 0. It gives me 1. Now that seems kind of dumb, but bear with me. The second row, I'm going to go with 1, choose 0. And that's also going to give me 1. But this one over here is going to be 1, choose 1, which is actually also going to give me 1. But he discovered there's a pattern. I'm going to write it out, and you guys can test me on this. This is actually, this number right here is going to be second, like this is the 0 row. This is the first row, this is the second row. So the second row, which I know is really the third row, choose 0. Second, choose 1. Second, choose 2. This would be the third, choose 0. Third, choose 1. Third, choose 2. Third, choose 3. Extrapolating this downwards, this now would be the fifth row, choosing 0. The fifth row, choosing 1. The fifth row, choosing 2. The fifth row, choosing 3. The fifth row, choosing 4. And the fifth row, choosing 5. Pascal discovered that his triangle was actually based on combinatorics, which kind of makes sense though, because when we started our class today and we worked with this, didn't I show you guys that really this sort of pattern right here can be done with a choose notation? So any single term that you want in Pascal's triangle, you don't actually have to write out the whole triangle. You just need to know which row you're on and add one less. Subtract one. Because technically this was this is the first row, the second row, the third row, the fourth row, the fifth row, the sixth row. So if we're looking for the seventh row, the way it's going to work is that this is going to be 6, choose 0, 6, choose 1, 6, choose 2, 6, choose 3, 6, choose 4, 6, choose 5, and it should always add up nicely. This last one should be 6, choose 6. And so all I need to do is use my calculator to figure out what half of those are. I don't even need to do them all. Why don't I have to do them all? Yeah, it's symmetrical, right? And so, like, I already know the first one here is going to be a 1, by the way, and this one over here is going to be a 1. And I know that 6, choose 1 is 6, so those ones are 6. So all you got to do is just figure out what 6, choose 4 is, which is the same as 6, choose 2, and find out what 6, choose 3 is. And now you've got this thing distributed like that. Absolutely brilliant. And it takes two things that you would think are unrelated, one of which is combinatorics, one of which is distributing and factoring, and there actually seems to be a link, which is really cool. So the question now, and this is where, if that made sense to you guys, is what sort of questions will be asked? So what I want to do then at this point here is I'll show you some diploma questions that they've asked in the past so you kind of know how to solve it. What's that? Okay, this is a formula that you are given on your formula sheet. And it looks very confusing at first. So you have to understand like what the heck is happening here. When you want to distribute something, there are 3 parts to the distributing formula. So I'm going to break it up into colors. This right here is your coefficient. This is how many of X you have, and this is how many of Y you have, and I guarantee they add to equal whatever the exponent is. Because let's look back, right? Let's look at some previous examples. Right here, you had 5 and 1. That adds to give 6. Here you had 4 and 2. That also adds to give 6. Here you had 3 and 3. That adds to give 6. That makes sense? So really there's 3 parts. You have the coefficient part, you have the y and the x part. And I started screwing up here and then I realized it didn't really matter. It doesn't matter whether you start with x and then y or do y then x. It really is the same thing. You know what I'm saying? So this is a formula that you can use. The hardest thing kids find about it though is that when you're looking for a certain term, it always has to be 1 less than you expect. And the reason why it has to be 1 less than you expect is you have to be able to start off with like say 8 choose 0. Because you always got to start with the choosing 0 value. So if you're looking for like the 3rd term in, you're actually looking for 8 choose 2. If you're looking for the 6th term, you're looking for choose 5. So let's try some examples here. Let's try expanding this guy right here. Now normally this would be a pain in the butt, but it's not so bad if you get the concept. Because there's a 5 right here, I can actually tell you there's going to be 6 terms. There was a question like this on your assignment. It was about how many unique outcomes were there for flipping coins. And if you guys didn't finish it already, I guess I'm giving it away, but the answer was, however many coins you have, add 1 more to it. We're talking about this? Yeah, that's this right here. I can tell you that there's going to be 6 terms when we're done. And I know there's going to be 6 because this is a 5 right here. The first term is going to be 5 choose 0, which is why it's 6, not 5, because you always got to start with 0. The next term will have 5 choose 1, then 5 choose 2, then 5 choose 3, 5 choose 4, and 5 choose 5. So that's my 6 terms. That's the first part. Each one of my terms has 5 choose something in it. Work? Well, then you just need to have a counter. For example, I'm going to need 2a 5 times, then I'm going to need 2a 4 times, then I need 2a 3 times, then I need 2a twice, and then I need 2a just 1 time. And on the last possibility, we're not going to actually have 2a. I'm just going to skip writing it. Which is really 2a 0 times, I guess. You see the overlap here in terms of we've done stuff kind of like this before. Then the last part of my term is the other value. And I do need to point out, see how there was a negative sign right there? It has to be accounted for though. So we now need to use negative 3b 0 times. We need to use negative 3b once, negative 3b twice, negative 3b 3 times, negative 3b 4 times, and negative 3b all 5 times. It's a little bit of a mess. So in my last step, I'm going to try to clean it up a little bit because it was getting a little bit crazy in terms of that. But can you guys follow how there's 3 parts to this? There's the X part, the Y part, and the choosing part.
Schubert, can you please come to the office? Ryland Schubert, please come to the office.
Does anybody know what 5 choose 0 is? 1. Okay. Now, this right here, because it's the power of 0, means we don't even need it. And this was 1, so we don't really need it either. So my final answer is 2a to the 5. But that's actually going to be this. It's actually 32a to the 5. Or 32a5. And the reason why is that the 2a, both of them have to go to the power of 5. So 2 to the power of 5 is 32. And a to the power of 5 is a to the 5. So you do need to take the 2 and times it to the power of 5 as well. So there's my first term. This would be known as T1, by the way. That's term 1. All right, let's say we want to find the second term. We need to figure out 3 things. We need to figure out the coefficient. We also need to figure out the x and the y values, or in this case, a and b. And a and b are easy. You're going to need 4 a's and one b. However, to figure out the coefficient, we actually need 3 numbers. Anyone know what 5 choose 1 is? Okay. But we also need to go 2 to the power of 4, which is 16. And then see how this b right here also came with a negative 3? We need to find what 5 from this times by 16 from this times by negative 3 is. 280? 240, okay. And so the coefficient now for this one is minus 240. The minus because there was a minus 3 there. Let me try some more examples here. Someone's tell me what 5 choose 2 is. Okay, so that gives us a 10. 2 to the power of 3 gives us an 8. And then minus 3 squared gives us positive 9. 10 times 8 times 9 is 720. And then for the last part, you need 3 A's and 2 B's. Oh wait, this one right here, I know is going to be 2 A's and 3 B's, but I got to figure out the coefficient. So 5 choose 3 is probably still 10, right? 2 squared is going to give us 4. And then minus 3 to the 3 is minus 27. Again, this one in my head, someone help me out here. 10 times 4 times minus 27. Okay, I'm going to have to go down because I'm running out of room here. The next term, I need 5 choose 4, which I know is 5. I need 2 to the 1, which is 2. And I need whatever minus 3 to the 4 is. So that's 81. 81 times 10, that should give me 810. And then that's the coefficient. Then the letters, you need 1A and 4 B's. For the final one, you need 5 choose 5, which I know is 1. Then you need to multiply it by 2 to the 0. But 2 to the 0 is still 1, so really this did nothing and this did nothing. I need someone to help me out here. What's minus 3 to the 5? And that's how many b to the 5s you need. We now foiled this thing out, and it was pretty intense, but we've now managed to foil it. Now, that was actually a pain in the butt still, but isn't it way better than trying to do it by hand? Absolutely, yeah. So I want to skip ahead here. Why don't I show you guys some of the diploma questions now? Because if you get the concept of how to do this, I should just show you how they've assessed in the past. So I'll skip these ones and we'll come back to them. Let's find this one here. Okay, so what they've done here is they've given you 3x squared minus 2y to the 3, and all of that goes to an unknown exponent. The exponent is 3k minus 9. When you're done, if you FOIL it out, you know how the last time around I had 6 terms? This one had 22 terms. Use that logic though. Yes, good, yeah. Go back here. You guys have the right idea. When there was 5 right here, because you have to count term 0, it was actually 6 terms. So if I tell you there's 22 terms, it means that this exponent was 21. Well, then all you gotta do is that 3k minus 9 was equal to 21. So, actually, it wasn't that bad. So that's one kind of question I might ask you about. It's a theory question where all you need to do is know that however much the exponent is, you get one extra term because you got to count the 0 term. So, here's another one. I'm going to tell you an unknown thing we're going to expand, m to the x, or mx minus 4 to the 8. I'm going to tell you what the term is. Our goal is to work backwards and figure out what the value of m happens to be. Now, one option is just to guess and check, because you could guess and check the 4 answers until you get it right. But let me show you a nifty trick you can play here. Let's say I was going to expand this out. I know there's an m sitting right there. I'm going to expand it anyways. If I want this term right here, I can figure out which term this was going to be. Because the first one is going to be an x to the 8. Then it would be an x to the 7. Then it would be an x to the 6. Then an x to the 5. And then an x to the 4. Which term are we looking for? The 5th one. Does that make sense? Because I'm looking for something with an x to the 4 in it, I'm looking for term 5, technically. But really, this is like 8 choose 0. This is 8 choose 1. This is 8 choose 2. This would have been 8 choose 3. This guy is 8 choose 4. To get the 5th term, we need 8 choose 4. You guys follow that logic? And I knew all of that because it told me there was an x to the 4 in it. So here's what I'm going to write out. I know that this should be 8 choose 4. Then I'm going to need mx. I'm going to need that 4 times. And I'm going to need minus 4 times. How do I know that they're both 4s? Exactly. They have to add to 8. And if 4 of them were x's, then the rest must have been these guys here. Well, I know that this is supposed to equal 145, 1520 x to the 4. I'm going to solve this now. Okay, someone help me out. What's 8 choose 4? Okay, and what is negative 4 to the 4? 256. Okay. Everybody okay with replacing these two numbers here with what actual numbers they are? I want to point out one thing right here. This middle term really means m to the 4, x to the 4. Because both the m and the x get 4s. And this is now equal to, again, 145, 1520 x to the 4. Now, the first thing that throws kids off is they're like, hang on, I need to solve for m, but there's x's. Why does it not matter? So the only things left you have to do is divide both sides by 70, divide both sides by 256, that gets rid of this guy and this guy, and then to get m by itself, 4th root. I don't know how to calculate it, but hopefully you guys can. So take that big number, divide by 70, also divide by 256, and then 4th root it. And hopefully it's one of our 4 answers. When you mark it yourself, so just start there, I guess. Did you guys get an answer? 3? 4th root?
No, because it's a positive.
Did I pass you one back earlier today? Didn't I?
Yeah, that was my assignment 3.
That was assignment 3. I haven't given you assignment 2 back.
No, you were going to mark assignment 2.
Oh, because I needed to mark it.
Yeah.
That's why. I'm sorry I haven't got to it yet.
Okay.
That's why. Sorry, did you guys figure out why you don't need to divide by the negative? When you 4th the negative number, it's positive? Okay. Everybody good on this question? Yeah, totally. Okay, so then it sounds like you guys got 3. Okay, so the key to solving this one, though, is to recognize that by it telling you that there was x to the 4, we knew that we were looking for this term right here, and that kind of got us writing the 3 different components of it. But you had to know which term we were asking for. Let's try another one here. We're going to expand this thing. They rarely, if ever, ask you to expand all of it, because expanding all of it is a pain. So all they're going to ask here is, just tell me what the coefficient on the x to the 12 term would be. So first we got to figure out, well, which one is the x to the 12 term. So I'm going to start writing them out here. See how this is x to the 3 to the power of 7? My first term is going to have x to the 3 to the 7, which would really be x to the, nope, that's 21, you multiply those. That's not the term I want then, is it? So it's not term 1. The next one would be x to the squared to the 6. That's the x to the 12 term. Oh, sorry, no, it's x to the 3 to the 6. That's x to the 18. My bad. The next one would be x to the 3 to the 5. That would give you x to the 15. It's not that one either we're looking for. We're looking for the 4th term. X to the 3 to the 4. It's the one that will actually give me an x to the 12. So that was the first step here, is that I need to know, look for term 4. Okay, now that I know that I'm looking for term 4, now I can start to write out what it would be. So term 4 means I need 7 choose 3, right? Because the first one would be 7 choose 0, 7 choose 1, 7 choose 2, 7 choose 3. So it's always offset by 1. That's the hardest things for kids to figure out. If you can get that, it's 7 choose 3, and then we need x to the 3 4 times, and we would then need negative 4. How many times? 3. How'd you figure that out? Because these two numbers have to add up to 7. Yeah. Okay. So help me out with the calculator. What's 7 choose 3? 35. Okay, this will give you x to the 12. What's minus 4 to the 3? Is that 81? No, it's not 81. That's 64. Okay. And so then of the coefficient, like numbers have to go together. We need the 35 times by the 64. Oh, good catch, because it's the power of 3. Good catch, Epi. It would be negative 64 because it's cubed. You're right. So right off the bat, I actually know it's got to be one of the negative numbers. Which one was it? The 2240. Good catch on the negative. I think in my mind I was doing 3 to the 4, not 4 to the 3, and that makes a huge difference. You guys follow that logic?
Yeah.
So this one here looks really intimidating. I mean, it looks intimidating. But bear with me for a second here. This basically says that you're going to have 1, 2, 3, 4, 5, 6, 7 terms. And the reason why you have 7 terms, right? 1, 2, 3, 4, 5, 6, 7 terms. The reason why you have 7 terms is because it was to the power of 6, and we know they always get 1 extra term. Now, look at this. This was x minus 1, which means that if we were actually writing it out, we're going to need to have, like, minus 1 will need to be done 0 times when x get used 6 times. Then we'll need minus 1 being used 1 time while x gets used 5 times. Sometimes I like to write this vertically because I find it's easier to see here. Then we'll need minus 1 twice while x gets used 4 times. Minus 1 3 times while x gets used 3. Bear with me while I just write it now. It's a 4 now. You guys see how I'm kind of writing out all of my terms? Rather than writing them in a row, sometimes I find it easier to write it vertically because I can see it a lot easier. What's the only thing I'm missing now? The first bit is the coefficient bit, right? So how many terms were there? 7 terms. But you have to count the 0 term, which means this should have been 6 choose 0. Oh goodness, that's not right. 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, 6 choose 6. So let's find out what each of these terms is. What's 6 choose 0? Negative 1 to the 0 doesn't really do anything, and then you need x to the 6. So what that means is that your first coefficient is 1. Keep it going. 6 choose 1 is 6. So you have a negative 1. It'll now make it negative 6, x to the 5. So this number right here is now negative 6. 6 choose 2, 10, 15. So that's 15. Now what is negative 1 squared? Positive 1. So that doesn't make it negative then, and then you'll need x to the 4. So it means that this number right here is 15. Okay, 6 choose 3. Is this the one that's 20 then? But it'll be negative. You guys are ahead of me because the negative to the power of 3 will make it a negative. That'll be x to the 3. So that's going to be a negative 20 right here. 6 choose 4 is back to being 15, and I believe it's positive. Then this will be negative 6 again, and plus 1. Sentence. Guys, all it was really asking you to do, this question here, is take all of your coefficients and add them up. So what is 1 minus 6 plus 15 minus 20 plus 15 minus 6 plus 1? That's what it's asking you to do. Okay. This one just randomly happened to turn out to be 0, by the way.
Oh, really?
Yeah, it was just random luck that it was 0. I think when they designed this question, they thought the kids would get really freaked out and be like, how can it be 0? But it happened to be that they all were zeros, right? If you forget your negatives, by the way, I think the answer becomes 64. Because 1 plus 6 plus 15 plus 20 plus 15 plus 6 plus 1, I believe adds to give 24. If you forget to include negatives on every other one of them. So I know that one looked really intimidating, but all it really wanted you to do is write out all of the terms and then just tell me, well, what's the coefficients in front of them when you add them up. Make sense? If a term in the expansion of this is this, let's find the value of m. We did one like this before. So let me try this one again. First thing we got to figure out is, well, which term are we looking for? If it's got an x squared and a y squared on the bottom, we got to figure out whether this is the first, second, third, or fourth terms. By the way, it only goes up to 4, right? Because if that's the power of 3, then there's only 4 possibilities, right? So let's start writing them out. The first one is going to be 2x squared all 3 times. The next one is going to be 2x squared twice, and the m over y once. The next term is going to be the 2x squared one time, and the m over y twice. And then the fourth term is going to be the m over y all 3 times. Which one of these terms am I actually caring about? The third one, yeah. So now that I know which one the third one is, now I just need to do one more thing. This is going to be 3 choose 2. The reason why it's 3 choose 2 is because this would have been 3 choose 0, this would have been 3 choose 1, this would have been 3 choose 3. So now I'm going to keep writing this out. 3 choose 2 is 3. I'm going to have 2x squared, and then I'm going to have m squared over y squared. And this was supposed to be equal to 54 x squared over y squared.
Why is it the third one?
Because we need a term that somehow has x squareds and y squareds. This one right here would have x sixes. This would have x fours over 1y. This one right here will have x squareds, and then it'll be over y squareds. I knew that only by looking at that bit there. Good question. Because it told me that this thing was going to be equal to 54x squared over y squared. So what I've done here, maybe I'm skipping too fast here. If you guys agree with me that this is the one we're looking for, what I did right here is I said, well, 3 choose 2 is 3. 2x squared to the 1 is 2x squared. And m over y squared is m squared over y squared. But in the top of the question, it said one of the terms is 54x squared over y squared. And so now that I know that it's equal to that, now I just need to solve for m, which, again, kids get freaked out because they're like, but I don't know x and y. I don't need to, because this x squared cancels that x squared. This y squared cancels that y squared. All you got to do is take 3 and 2, make it 6. Divide both sides by 6. M squared will equal 9 when you square root it. M was 3. So there you go, M was 3. Is that my last one? Okay. You guys wrote a quiz last week. The quiz I'm going to give you guys on Wednesday, it only adds this. Okay, like I will put these questions on there, but I need you guys to know on your diploma, you are going to get one of these and probably only one of these questions. Yeah. Right. Because the way the breakdown works is that your diploma is 40 questions. 6, maybe 7 of them are on permutations and combinations. Of those 6 or 7, it's probably just one that's on this topic here. So if you feel like you get the concept, the question is just like, how are they going to ask you to solve it? Right? And so if you kind of get the 3-part concept, I rarely use this formula, but there is a formula you can use. Right? To find any term, you need to know this portion, and this portion here. So long as you kind of get that concept, I usually just write them out, and I like to stagger them so that I go 8, choose 0, then I write 8, choose 1, then I write 8, choose 2, then I go x to the 8, y to the 0, x to the 7, y to the 1, x to the 6, y to the 2. You know what I mean? I just kind of make a chart, and then just figure out whichever term they're asking me for, and then I just need to figure out which one of the 9 there is that I need to solve for. That's our last lesson in this section. So, like I was trying to start class with, the only thing I have left to teach you guys then is trig. And I'm going to try to do it in 6 lessons. So we should be able to do this by Christmas. We're going to do probably 2 or 3 lessons joined with the 20-ones, and I'll do 3 extra lessons that are just for you guys. So, but I want to do a really thorough job of redoing 20-1, because if you don't remember the stuff I taught you last year, that doesn't really help. So anyways, that's our plan. So tomorrow's a work day. Wednesday we'll write 1 more quiz. Thursday, Friday I'll give you work days, and next week Monday we'll try our unit test. And that's it for our unit. Well, no, I'll teach you the trig stuff. Calculus or chemistry. All right. Anyways, all right. That's our lesson.